Okay, hello everyone. So in this part 4, we'll be learning about fringe separation. So how do you find the fringe separation? So basically in our outcome, we need to know how to derive the fringe separation. And the fringe separation is actually lambda L over D. Okay, this is the pattern that we will see from Young's double-slit experiment. On the perpendicular bisector, you'll see constructive interference. This is known as a central bright fringe, or is also known as the zero-order constructive interference. And this is your first-order constructive. This is your second-order constructive. This is your first-order destructive, second-order destructive, third-order destructive. So fringe separation is basically the separation between adjacent maxima. So it can be the distance between the central and the first-order maximum. Or it can be between the distance between the first-order maximum to the second-order maximum. Or it can also be between the first-order minimum to the first-order minimum. So this here is known as fringe separation delta Y. Okay. So to derive this, all right, if we draw a triangle from the perpendicular bisector to, say, the first-order constructive interference, and we label this as L. So L is the distance, right, between the double slit to the screen. And typically, right, L is very much larger as compared to the double slits. So the double slits can be, let's say, 0.5 millimeter apart, and L can be like 1.2 meters, right? So theta is the angle between the perpendicular bisector to the point where you see the first order constructive interference, right? So this is known as your angular displacement. So using trigonometry, tangent theta is delta y divided by L. So delta y is here divided by L, the opposite. And since what we see here is constructive interference, we can describe the path difference between the two light sources to be d sine theta equals to m lambda. So m lambda represents constructive interference. However, we see that this is the first order constructive interference. That means m has to be 1. Or I can write it as sine theta, which is 1 lambda divided by d. Okay, in the case of Young's double slit, theta is actually very, very small. That means the fringe separation, delta y, is very small in comparison to L. So this here can be in the region of 1 millimeter, right? Whereas this here will be in the region of 1.2 meters. So when you use this to find tangent theta, you find that tangent theta is actually very, very small. So in the case when theta is very, very small, we find that tangent theta is approximately equals to sine theta. So if you key a small value of theta into your calculator, you find sine tangent, let's say 0.01 degrees, is actually the same as sine 0.01 degrees. All right, this is true if theta is very, very small. So we can equate tangent theta, this tangent theta, to sine theta. And rearranging, we get delta y, which is lambda L over D. So delta y is known as your fringe separation. L will be the wavelength. L will be this distance, the distance between the double slit to the screen, and D will be the separation between the two slits. And delta y can also be between adjacent minimum. All right, so we have already derived the fringe separation. Next, let's solve problems, right? Using d sine theta equals m lambda and delta y is lambda L over D. And determine the wavelength of monochromatic light from measurements of two slit interference pattern. Okay, so let's try questions. Okay, try this question first before proceeding with the video. All right. 4 minutes. Time yourself as well. Okay, so let's discuss this question. When mercury light with a wavelength of 436 nanometer was used in a double slit experiment, the first order maximum was observed at an angle of 0.0229 degrees. So when this light was replaced by a source of unknown wavelength, the third order minimum was observed at 0.0344 degrees. So in part A, right, what's the wavelength of the second order light source? Okay, so there are two parts of this question. So the first part is we have to solve it for 436 nanometer. And we know that it experiences constructive interference because it's a maximum, all right? Maximum, right? So for constructive interference, we describe it as d sine theta equals to m lambda. And since we are describing the first order constructive interference, we can set m to be 1. So the first part of this question is we have to find d, the separation between the two slits. So since you're given m, lambda, and theta, we can find the value of d. So the slits are basically about 1.09 millimeters apart. Okay, in the second part of this question, all right, once we have d, we can use this information to find the unknown wavelength. But take note, when you use an unknown wavelength, you observe a third order minimum. Okay, minimum is destructive interference. That means to describe destructive interference, we have to use this formula d sine theta equals to m plus half lambda. So the path difference must be m plus half lambda. And the third order minimum. So what's the value of m for the third order minimum? Yes, m has to be 2. So substituting m to be 2, we get as 2.5. So we know d, we know theta, and we know this is 2.5. We can find what is lambda. So substituting the values and finding lambda will be 2.62 times 10 negative 7 meters. That's your lambda. Okay, in B, right, in what region of the electromagnetic spectrum is this found? Okay, to answer this, it will be good, right, if you know the visible spectrum. So the visible spectrum ranges from 400 nanometer at one end of the spectrum and 700 nanometer at the other end of the spectrum. So 400 nanometer is violet and 700 nanometer is red light. And the rest of the colors ranges from 400 to 700 nanometer. So it's good if you remember this, all right? So that in the case when they ask you in which part of the electromagnetic spectrum is this light found. So since this is equivalent to 262 nanometer, okay, nanometer is times 10 negative 9. So this is equivalent to 262 nanometer. So it's smaller than 400 nanometer. So it lies in the region of ultraviolet radiation. So light is always represented in terms of nanometer. Okay, let's try example 5. So pause the video, time yourself for 3 minutes before continuing. Okay, in this question, the diagram below shows two coherent sources of wave S1 and S2. So the sources oscillate with a phase difference of 0.5 lambda. So this means when the two light source comes out, right, one from S2 and the other one that comes out from S1, the moment they come out, they already have a phase difference of 0.5 lambda. So the source each generate a wave of wavelength of 2 centimeters. So each source produces a wave that has an amplitude of x0. So the question is, what's the amplitude of oscillation at point B? Okay, so how do you answer this question? Okay, let's visualize, right, what happens. Right? So let's assume that S1, the wave that comes out from S1, is a crest. And the light source that comes out from S2 is a trope. So this is what it means, right? When the two waves comes out from their respective sources, S1 and S2, they already have a path difference of 0.5 lambda. Can you see they are phase shifted by 0.5 lambda? So in this case, what's the amplitude of the wave when these two waves meets up at point P? Okay, let's consider this, right? The light source that come out from S1 has to travel 5 meters before it reaches point P. So in terms of lambda, because 1 lambda is 2 centimeters, basically it has to travel 2.5 lambda before reaching point P. So let's assume that this is where the wave comes out. So it has to travel 2.5 lambda to reach point P. So we can count that this is 1, 2, this is 3 lambda. So half of it will be 0.5. So that's what you get, 2.5 lambda. So when the source comes out from S1, it travels 2.5 lambda to reach point P. Okay, when the light source comes out from S2, it has to travel 13 centimeters to reach point P. So in terms of lambda, we divide it by 2. So in other words, it has to travel 6.5 lambda to reach point P. So if we visualize from here, right, that means S2 is actually traveling 6.5 lambda before it reaches point P. So can you see, this is 1 lambda, 2, 3, 4, 5, 6, and 6.5. Right? So S2 comes out earlier because it has to travel longer to reach point P. So what's the path difference? So the path difference is actually this thing. Can you see from here to here represents the path difference? So the path difference will be 1, 2, 3, 4 lambda. So S2 has to travel 4 lambda longer as compared to S1. So what do you see at point P? Is it constructive or destructive? In this case, right, you see a crest from S1 meeting with a throw from S2. So in this case, you will see destructive interference. So the amplitude will be 0. Okay, so take note, the reason why now when I have an integer lambda, I get destructive interference is because, right, when the two wave comes out at point S1 and S2, they already have a path difference of 0.5 lambda. So they maintain this constant phase relationship until they reach point P. So you can see from here, right, when they maintain a constant phase relationship, a crest from S1 will always meet a throw from S2. Okay, so there was once a final year exam question, right, that tested you on this, right, where they shifted the phase between S1 and S2 that comes out. So if the two waves are in phase, let's say S1 is a crest and S2 comes out as a crest as well. So they are in phase with one another. So if S1 takes 1, 2, 3 lambda to reach point P, and S2 takes 1, 2, 3 lambda to reach point P, so the path difference between them is actually 0. And what we see on the screen would be constructive interference because there's a crest from S1 meeting with a crest from S2. Okay, in this case now, what happens if there's a path difference between them? So the path difference between S1 and S2, we can say that it is 1, 2 lambda. So S2 starts 2 lambda ahead compared to S1. So to reach point P, S1 takes 3 lambda, S2 takes 5 lambda. So the path difference is 2 lambda. And what do we see on the screen will be constructive interference because it's a crest from S1 meeting a crest from S2. Okay, that question just now was basically testing you on the concept. So you need to understand the concept, right? So do not just memorize and say, oh, if the path difference is 0, I will always say constructive interference. Okay, so in this case, what happens if the two waves that comes out, they already have a path difference of 0.5 lambda. So S1 is going to take 3 lambda to reach point P, and S2 is going to take 3 lambda to reach point P. So when they meet on the screen, what happens will be a crest from S1 meets a throw from S2. So the path difference is 0, but the outcome is totally different. You see destructive interference. Another example would be S1 and S2. So at this point, the starting point, S1 is a crest and S2 is a throw. But the path difference will be 1.5 lambda, right? Can you see this is 1.5 lambda. So there's a path difference between them of 1.5 lambda. But what do I see on the screen will be a crest from S1 meeting with a crest from S2. I will see constructive interference. So take note the question, right? When the two waves comes out, are they out of phase or are they in phase? The outcome will be different. Okay, so basically, Young's substitute, right? We use this formula d sine theta equals to m lambda to describe regions of constructive interference. So if you're considering the zero order constructive, m will be 0. If you want to describe the first order constructive that is here, first order constructive, m will be 1. You want to describe the second order constructive, m equals to 2. Destructive is basically these black spots here, right? The dark spot. And destructive interference is described as d sine theta equals to m plus half lambda. So if I want to describe the first order destructive interference, so this is your first order, or this is also your first order. So what's the m value that I should substitute? I should substitute m equals to 0, right? Because m is an integer. So it always starts with 0, 1, 2, 3, 0, 1, 2, 3. So I want to describe the third order destructive interference. I substitute m to be 2 in this formula. And what you have just learned is fringe separation. It's just pattern separation. So it can be between adjacent maximum, or it can be between adjacent minimum. So it can be between this, let's say, fifth order maximum and the fourth order maximum. We describe it by using this formula. Right? So any adjacent maximum or any adjacent minimum, that's known as your fringe separation. Okay, next, let's try another question. Okay, pause this video for 3 minutes, try it, and then resume playing after 3 minutes. Okay, so let's discuss this question. In a double slit interference experiment, light of frequency 6 times 10 to the 14 Hertz is incident on a pair of slits. So bright fringes are at 3 millimeter apart as observed on the screen some distance away. So what is the separation between the bright fringes when the frequency of the light is changed to 5 times 10 to the power 14 Hertz? Okay, to answer this question, we use the fringe separation formula. That is delta y is lambda L over D. Okay, in this question, we only change the frequency, nothing else, right? And frequency is related to lambda by this formula. Because when we see from this formula, right, there's no frequency. So we have to represent frequency in terms of lambda by using this, what we have learned in electromagnetic wave. So let's take, for instance, fringe separation 1, right? This is fringe separation 1. It's given as C over frequency 1 times L over D. And we know that fringe separation 1 is given as 3 millimeter. Now, when we change the frequency of the light, basically we're changing lambda. So when we change frequency, the fringe separation is going to change. So the new fringe separation is given as C over frequency 2 times L over lambda. So dividing this, right, delta y1 over delta y2 is basically dividing the first term, that is the first term here, divided by the second term. So you want to multiply, we just invert this thing, right? Okay, now we can cancel off common factors. Of course, the speed of light didn't change, so we can cancel that off. We can cancel off L. So L is the distance between a double slit to the screen. We didn't change that. And we didn't change D. So D is the separation between the two slits. So what we get now would be the ratio of the fringe separation with ratio of frequency. So since we know delta y1, which is 3 millimeter, we can use this ratio of the frequency to find delta y2. So delta y2 will be the ratio of frequency times delta y1. So it's 3.6 millimeter. Okay, let's try this question. Pause this video for 4 minutes, try it, and then resume after 4 minutes. Okay, in this question, monochromatic light is incident on a pair of narrow slits, a distance 0.1 millimeter apart, right? So this is D, 0.1 millimeter apart. A series of bright and dark fringes are observed on the screen, a distance 2 meters away. The distance between the adjacent bright fringes is 8 millimeter. So between a maximum and the subsequent adjacent maximum, the distance is 8 millimeter. So in this question, what's the path difference between the light waves from the two slits that meet at the second order dark fringe? Okay, so to answer this question, okay, what is given is the slits are 0.1 millimeter, and you are given delta y, which is 8 millimeter. So basically, delta y is given and d is given. So we can find lambda. L is also given. This is L. So solving this, delta y, d, and L, we can find lambda will be 4 times 10 negative 7 meters. All right. So the question asks us, all right, what is the path difference between the two light sources that comes out from here to the second order dark fringe? So we have found lambda. How do we find the path difference? Okay, the path difference, right, for second order dark fringe, the path difference is given as d sine theta. Right? This is known as a path difference, d sine theta. So since we are describing the dark fringe, that means d sine theta must be equals to m plus half lambda. Because dark fringe is destructive indifference. And what's m? It's a second order dark fringe. So what's the value of m? That means m has to be 1. So substituting 1 into this formula and lambda, we can find the path difference. So the path difference between the two light sources to the second dark fringe is 6 times 10 negative 7 meters. So this means that S2, the one that's below here, has to travel slightly longer as compared to the light source S1. So the question is how much longer? It has to travel 6.0 times 10 negative 7 meters longer as compared to the light source from S1 in order for them to meet at this point on the screen to cause the second order destructive interference. Okay, so we have tried few samples, all right, where we use this formula, fringe separation as well as constructive interference pattern. And I also gave you a few examples where we use this formula to find the wavelength of an unknown light.